Hello class. So today we're going to do 11.6 Absolute Convergence and Ratio and Root tests. So first thing we're going to start off with is the Absolute Convergence, and the definition says that if we have a series, it's called an absolutely convergent if the series of the absolute value is convergent. So let's demonstrate that for you. So we can see that this function here is an alternating series, right? It's going to be 1 minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared, and so forth and so on. So what we're going to do is we're going to take the absolute value of this function and see what happens. So if I take the absolute value of this, what's going to end up happening is the alternating series is going to drop, and so I'm going to have a series that goes from 1 to infinity of 1 over n squared, and that's going to be 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so forth and so on. Well, this series should look very familiar to you now. We know that this is going to be convergent, and the reason that it's convergent is because this is a p-series, and it's a p-series with a p equal to 2. Now, remember, going back to p-series, you're able to tell when something is convergent or divergent by looking at the exponent. So please make sure to review that so that you completely and thoroughly understand that, as it will be used quite a bit. Okay, let's do another example. So this is another example with the alternating series, and let's see if we can determine if this is going to be convergent. So let's see. So if we're going to do this, we know it's a harmonic series. So it's going to be oscillating back and forth, right? And we know that this is convergent. It's already told us that. So now what we're trying to do is see that if it's absolutely convergent. So to see if it's absolutely convergent, we're going to take our sum of the absolute value of this thing and see if we get something that is going to be absolutely convergent. So it's going to end up being 1 over n, and we know that 1 over n is 1 plus 1/2 plus 1/3 plus 1/4 plus so forth and so on. But this is also a harmonic series, but this harmonic series is going to be divergent. And the reason the absolute convergence is divergent, it fails it, is because this is, again, it's a p-series, and this p-series has a p equal to 1, and that's what makes us get this divergence. So it's important, again, like I said, knowing our p-series so that you can reference it to be able to solve these types of problems. Okay, let's go on to another example. A couple definitions before that. We can have conditional convergence, and conditional convergence is kind of like what we just showed. It is convergent but not absolute convergent. So the one that I just showed you there was that conditionally convergent, and that's important. Now, one of the things that we know that's important too is that if something is absolutely convergent, then the function itself is convergent. So if it's absolutely convergent, the lesser is convergent. But if it's convergent, that doesn't mean it's absolutely convergent. So it's important that you understand the distinction between the two of them. So let's look at this example here. We have a series that's going to go for cosine of n over n squared, and we need to determine if it's convergent or divergent. So I'm going to use my absolute convergence to see what happens. So I'm going to go cosine of n over n, and that's going to be equal to cosine of n in absolute value over n squared. This should be squared 2 here, sorry. But we know something really, really cool. We know that since absolute value of cosine of n, that's going to always be less than or equal to 1 for every value of n, right? That symbol means for all, for every value of n. So instead of using the smallest values for n, I'm going to use its largest value. And so I'm going to say, all right, so cosine of n in absolute values over n squared is going to be less than or equal to 1 over n squared, correct? By using that reasoning that I just said to you. So that means then, if I have a sum from 1 to n squared, right, from 1 over n squared, this is convergent, right? It's convergent because it's a p series, and my p here is 2, right? The exponent here is 2, so that's telling me that this thing is bigger than 1, and so we know it's going to be convergent. So since that's the case, that's bigger than cosine of n over n squared, we know then that implies, therefore, that my sum of cosine of n over n squared is convergent, right? And this is done by the comparison test, right? Comparing one to the other. We've done that. And so if that's convergent, then this implies that the non-absolute would also converge. And so this is convergent. So you can see there's a lot of reasoning that's going on here with these problems. And we're using information that we've had in the past to be able to help us understand how to be able to move forward. So understanding your p-series is important, understanding comparison tests from the previous section, and then understanding that if something is absolutely convergent, then the non-absolute would also be convergent. Okay, we also have tests for the ratios, and so the ratio test tells us when we compare the next term over the previous, right? That's what it's saying here, next term over the previous in absolute values. If that's equal to some limit L that's less than 1, then we have absolute convergence, and therefore we have convergence for our series. If it's bigger than 1, or if the limit goes to infinity, then we're going to have divergence. But the ratio test, unfortunately, doesn't help us if we're equal to 1. So that means we have to do some other things, and I'll demonstrate that for you. Let me go ahead and do an example that you might understand, and then we'll slowly build on that, okay? So here we go. So in this example here, we're going to do the ratio test, and so for the ratio test, I'm going to go the absolute value of a of n plus 1 over a sub n. So that's going to be a negative 1 to the n plus 1 times n plus 1 cubed over 3 to the n plus 1 over a negative 1 to the n cubed over 3 to the n, and that's all in absolute values, correct? So trying to clean that up, I'm going to get n plus 1 cubed over 3 to the n plus 1 times 3 to the n over n cubed. This will clean up to be 1/3 n plus 1 over n to the third. And this can actually be cleaned up even further. So it's going to be 1/3 1 plus 1 over n to the third, which we know that as we take the limit of this thing, we're going to get a value of 1/3, and that's less than 1, right? Now, what does this mean for us then? Since it's less than 1, we have these values here. What does that tell us? That's the first case. It's going to be absolutely convergent. So since it's absolutely convergent, we know that by the ratio test, the given series is absolutely convergent. And since it's absolutely convergent, the non-absolute is convergent as well. So there it is. But it's all about manipulation, and we have to remember what I did here is I took the limit as n went to infinity, so this went to 0. 1 cubed times 1/3 is 1/3. That's less than 1. And then by the ratio test, I was able to make a call on that. Okay, let's do another example. So in this example here, I'm going to go a to the n is n to the n over n factorial. And then I'm going to go a to the n plus 1 over a to the n is equal to n plus 1 to the n plus 1 over n plus 1 factorial over n to the n over n factorial. That's going to clean up to be n plus 1 times n plus 1 to the n over n plus 1 times n factorial times n factorial n to the n, right, multiplying by the reciprocal. So that should clean up to be the n's are going to cancel, and I'm going to end up with n plus 1 over n to the n, right? And that's going to give me 1 plus 1 over n to the n. And then we're going to take the limit of that, right? And so the limit as n goes to infinity of 1 plus 1 over n to the n is going to equal e. It's approximately e. You probably don't remember that, but that's from chapter 3 in your book, 3.2 to be exact. That is the definition for e. So what we see is since e is greater than 1, in fact, chapter 3, section 2, you'll be able to find the definition of that. Since e is greater than 1, right? E is greater than 1. That's the second case. It tells us that we're going to be divergent. And so, since that's greater than 1, the given series is divergent by the ratio test. Okay? Very cool. Okay. Let's go on to the next. Here is the root test. And so again, we see if it's less than 1, it's convergent. If it's greater than 1, it's divergent. If it's equal, we're inconclusive. And don't worry, I'll do some examples of inconclusive. I think I incorporated it in my notes from 11.8, where I really delve into showing the inconclusive cases for root and ratio test. All right, so for this one, again, we can see we're going to be looking at the absolute value of this thing and see what happens. So let's go ahead and see what happens. All right. So I have a to the n is equal to 2n plus 3 over 3n plus 2 to the nth. But since we're trying to do a root test, what I'm going to do is I'm going to take the root of both sides, And so what I'm going to end up with is the nth root of a to the n is 2n plus 3 over 3n plus 2. That's going to be dividing everything by n. Ooh, that should be a 3 over n. And then 3 plus 2 over n. That's going to give me, as the limit goes to infinity, 2/3, which is less than 1. So that tells me that this here is going to be what? Oh, wonderful. We know that this will be absolutely convergent, right? And therefore, it will be convergent by the root test. All right? This is actually a pretty cool, short and sweet section. Nothing too crazy about the convergence. It's something that I believe you should be able to handle quite easily. It's just a matter of remembering the steps to it. So make sure that you have your notes with you when you're trying to do these problems, and you should be able to fly through them. All right. Wish you all the best. Take care.